Okay, hello and welcome to this 17th lecture on cyber-physical system fundamentals, where we're going to teach you the fundamentals of embedded systems technology that is used in cyber-physical systems. So today we have two topics, and the first topic we are going to discuss today is the mapping of applications to executable platforms. So as you see, we're proceeding in the structure of this course as we've already seen in the previous iterations of this lecture. So we now arrived in chapter 6 of the accompanying textbook, the chapter on application mapping. So what problem are we trying to solve when we are mapping applications to platforms? Now consider you're using some kind of complex networking application like the one shown in the top left corner here. So you've seen there are several processing steps denoted by the various circles here, and there is data flow between these processing steps. So you have some certain set of dependencies between these steps, so certain directions in which the data must flow, in which order some information must be processed here. So the task of mapping applications to platforms is to consider all this complexity of this application and to build a mapping so that it can be executed on some hardware platform that is given, which is shown in the lower right corner here, which may consist of several processors, several interconnects, different memories, processors with different properties like RISC processors or specialized processors like DSP or even hardware accelerators. Now, if we consider embedded systems compared to PC-like systems, what are the main differences between mapping applications to these two very different platforms? Now, on the one hand, the PC-like platforms have certain properties that are very common, that you can buy in every PC, whereas embedded platforms are more customized. And this reflects in all these points here. So on the one hand, we have the architectures for the PC-like systems. You know that you can buy a PC and all the software you have for your present PC is probably going to run on your future PC. And this is based on the fact that the architecture of these PC-like systems are mostly homogeneous. They are not compact, so they are using complex CISC processors like the x86. They're using a defined set of bus systems of interfaces. And even if new technology comes along, great care is taken to ensure compatibility so that when you upgrade to some newer piece of hardware, your older interface cards, your older drivers, your older software keeps on running. Embedded systems, on the other hand, are tailored to some very specific application usually. So we can actually make use of the fact that we know what is going to run on this and that we often don't have any legacy obligations. So the architectures for embedded systems are frequently heterogeneous, so to adapt to a specific part. So signal processing tasks in an application are better executed on a digital signal processor. Other parts may better be executed on some standard RISC processor. These architectures are frequently very compact also, because you don't have that much chip space, that much money to spare on these architectures. Accordingly, the compatibility with pre-existing binary software is less relevant for embedded systems because you usually decide on a new application, you devise a new application, so compatibility of existing libraries is less relevant for embedded systems. Of course, for PC-like systems, it's very relevant because you want to run your well-known applications like Microsoft Office and so on. So, essentially, the cause from this is that the architecture for PC-like systems is fixed, more or less. It can evolve, but it's bound by very strict compatibility rules, so it only has certain ways to evolve. For embedded systems, the architecture is sometimes not fixed. It may change. It may even change in some systems on the fly because some systems can actually be reconfigured while they're running. So the next question is, what models of computation, as we've seen in the second chapter of the companion textbook, are actually used? So on PC-like systems, we usually are using the commonly known programming languages like C, C++, or Java, which all base their execution on a von Neumann model of computation. In embedded systems, we can actually profit from the fact that we can have more grades of liberty here, so we can often use C, but we can extend C with multiple models like data flow, with discrete event models and so on. We can also use different modeling approaches like we've seen in the previous chapters, like state charts and so on. So one really important distinction, as we've also already seen, are optimizations. So for PC-like systems, often the average performance is the only optimization criterion that's applied, whereas for embedded systems you have quite a lot of criteria that you have to consider, like energy, like cost, like size, like temperature, and so on. Accordingly, one criterion we've considered before, the real-time performance or the real-time criterions, are very often not important at all for PC-like systems because you don't do any timing critical stuff on these systems. On the other hand, for embedded systems, real-time is one of the dominant factors when trying to do system design and system optimization. So for embedded systems, real-time is one of the predominant criteria. The applications for PC-like systems, well, you mostly use a single application or a couple of predefined applications, like your web browser, like your Office word processing system, and so on. In embedded systems, you often have to react to several external circumstances, so you have several concurrent applications that have to be running at the same time, whereas on the PC, you usually concentrate on the application in the foreground, let's say the web browser, and even if you have an application running in the background, like a word processor, it's often just idling around waiting for you to activate it. And so, of course, the last point is related to this. Well, on a PC, you can load any application you like. So only some of the applications are actually known at design time of the system. Most of the PCs will be running Windows, will be running Word, but many people are using custom applications like Photoshop or AutoCAD or stuff like that. And of course, you can't optimize for all of these, so you really can't make use of the fact that some applications are known. On the other hand, in embedded systems, if we're not considering smartphones, most of the applications are actually known at design time because the software is mostly fixed. So you know which applications you put on the system, and of course you can benefit from that. So, what is the problem in mapping applications to execution platforms? The designer is giving, on the one hand, a set of applications. Together with these applications, there comes a set of scenarios that describe how these applications will be used. So perhaps some predefined limits to input data, to input values, and so on. And you often give a set of candidate architectures, which comprised of processors, which might be heterogeneous, of communication architectures, which also might be heterogeneous, and of a set of possible scheduling policies. Now, given all these prepositions, the designer has to find a mapping of these applications to the processors in the system, an appropriate scheduling of the task to the time in the system and the processors, if this is not fixed and predefined, and a target architecture if we want to perform some design space explorations, so if the target architecture isn't fixed from the beginning. And of course he has to consider a set of objectives, so he has to keep the deadlines for ensuring the real-time conditions, or he might have to maximize the performance for some really performance critical stuff like video decoding, or perhaps both at the same time. And of course he might have to keep a watch on different objectives, like minimizing cost or energy consumption of such a system. So, of course, you can see this is a complex task, and if you're trying to do this task by hand, you're quickly overwhelmed by the many possibilities, by the complexity of this problem. So one important thing here to handle the problem of mapping applications to execution platforms is that we need tools that help the designer to automate the process, to really make use of automatic evaluation of certain criteria, automatic optimization of certain criteria, to help find the optimal solutions that the designer wants to consider. Of course, this is not only the topic of recent research, but this has been the topic of research that's ongoing since several decades here. And our working group actually is part of the Artist Design Network, where we are organizing a specific workshop on mapping applications to multiprocessor systems on chip, which takes place at Rheinfels-Castle, which is located at the Middle Rhine Valley. Quite a beautiful location, so people love to come here and discuss on mapping applications. So we have a long history here from 2008 to the current time. We have yearly conference or workshop on this topic with quite a couple of international participants, and we also had a special session at the Embedded Systems Week in 2011, where some of the most important people in the area actually participated. When considering mapping applications to embedded systems, there's quite some related work in adjacent areas that we can consider here, because we can actually learn from this and we can also retroactively apply the methods we develop here to these problems. So in automotive design, you have the problem that you have lots of embedded control units, so-called ECUs, and these embedded control units each have to execute a certain task, and these are interconnected by several bus systems. So mapping of the complex set of applications in your car, like an anti-lock brake system, ESP, the entertainment system, and so on, to the different processors in your embedded control units is a very similar task to what we are doing here. Scheduling theory actually is a mathematical theory that provides insight for the mappings of tasks to the assigned start times. So what's the best or even latest point in time when we can actually start a task to keep our deadlines? Hardware-software partitioning is an area of research that actually decides which part of an application has to be implemented or can be implemented in software, and which part of an application can be implemented in hardware, and you can shift the barrier around in order to optimize, especially if you have multiple processors in your system. High-performance computing, or HPC, is an area where large numbers of processors are available, and so of course you want to automatically parallelize your sequential applications. Methods for these parallelization approaches exist, so you can actually parallelize some sequential application, but this only currently works for single applications, for a fixed architecture, often with no support for scheduling, and you usually have vastly different memory and communication models in these high-performance computing clusters than in your typical embedded system. Another important area that's related is high-level synthesis. High-level synthesis provides useful terms that we can use to discuss, and even algorithms like scheduling, allocation, and assignment. And of course, the last point we want to consider here is optimization theory, because actually we want to optimize some parameters, let's say for energy or for worst-case execution time. So when we consider useful terms from hardware synthesis, we have actually 4 terms we consider. Sometimes 2 of these terms are actually taken or considered together. The first one is resource allocation. Resource allocation concerns the decision which type and number of available resources are available. Resource assignment then maps a given task to a given hardware resource. The binding describes a mapping from some behavioral description to the structural domain. So for example, it binds a task to a certain processor, or it binds a given variable to a certain memory location or a certain type of memory. And finally, scheduling defines a mapping of tasks to assigned start times of these tasks. Sometimes, as I said, this resource assignment we've seen above is considered to be included in the scheduling step, so this would reduce this to 3 terms that are relevant here. So which classes of mapping algorithms are interesting for us? Which classes do we want to consider in this course? Now, first we start off with the classical scheduling algorithms. These are mostly suited for independent tasks. These often or mostly ignore communication, and they are mostly only suited for single homogeneous processor systems or homogeneous multiprocessor systems. If we have dependent tasks, like those considered in the architectural synthesis, we can add some more complexity here. This scheduling approach or mapping approach was initially designed in some different context, but is also applicable here. Hardware-software partitioning defines dependent tasks. It can address the problem of heterogeneity in systems, and it will focus on resource assignment. And finally, design space exploration using evolutionary algorithms will also be able to consider heterogeneous systems. And here, due to the complex genetic algorithm approach we can also afford to include communication modeling to get a more precise idea of what's going on in our system here. So, let's start with real-time scheduling. We start off with a given task graph. The graph G consists of a tuple, and this tuple has two elements, a set of vertices V and a set of edges interconnecting these vertices E. So we define a schedule tau of this graph G to be a mapping of the set of vertices to some given deadlines for tasks. And this might look like that. So we have a graph here with dependencies. You see we have 4 vertices, V1 to V4. And you see we have a dependency of V2 to V1 and a dependency of V4 to V3. So V2 can only start when V1 is finished. And on the other hand, V4 is only able to start when V3 is finished. And on the x-axis here, we have a given set of times and a given set of deadlines. So let's say we start off with V1, so we can map V1 to be executed here. The task V2 is delayed, so in between we can add a starting point for V3. Then we can add V2, and finally we execute V4 and have all the tasks executed. So typically the schedules we define, and the schedule is the number of arrows going from the vertices here to these points in time on our deadline schedule. These schedules have to respect a number of constraints, including resource constraints, dependency constraints, and deadlines. And the task of scheduling is to find such a mapping that fulfills all the constraints we give it. So taking care of real time is really important here. Which kind of deadlines do we consider here? In general, when working on real-time scheduling problems, you distinguish between 2 sets of deadlines. On the one hand, you have soft deadlines. A soft deadline is something that's actually not as critical if it is not kept. And we distinguish between the hard deadlines. A hard deadline is actually a deadline that, if it is not kept, would lead to a catastrophe. This is defined by Hermann Koppitz again. You've heard his name before in the previous lectures. And so a hard deadline is really something you will not miss, or you don't want to be able to miss, just because, otherwise something might go severely wrong. And all the other time constraints, as we said, are called soft. So in this course, we will focus on the hard deadlines. Which kind of tasks do we consider here? Now, in hard real-time, we distinguish between 2 kinds of tasks. And the first one is the class called the periodic tasks. So tasks which must be executed once every p units of time are called periodic tasks, and the period of these tasks is that p we defined just above. And each execution of a periodic task is called a job. So you see here the little metronome in the animation, which says it has to be executed regularly in order to keep the constraints. All tasks which are not periodic are called aperiodic tasks. And a specific set of these aperiodic tasks are the so-called sporadic tasks. So tasks requesting the processor at unpredictable times are called sporadic if there is a minimum separation between the times at which they request the processor. So they're actually not sporadic if they use up all the processing time in the system. So if we have periodic on the one hand and aperiodic on the other hand tasks, so what kind of scheduling can we actually apply here? Now, on the one hand, we have the so-called non-preemptive scheduler. The non-preemptive scheduler is a scheduler which does not take the CPU away from the processor. So when it starts a task, it continues to execute the tasks until it is finished, which might result in a rather long response time. And you see non-preemptive schedulers are available for periodic as well as aperiodic schedules. And on the other hand, we have preemptive schedulers. Preemptive schedulers take away CPU time, take away resources forcibly from an executing task, so they don't wait until a task is finished. These can be used if some tasks have really long execution times, or if we require a short response time of the system to external events, because we can then schedule the event, the task to handle that event more or less immediately. So the next question that remains is when to perform the scheduling. On the one hand, we can have dynamic scheduling, so the processor allocation decisions, the scheduling itself, takes place at runtime, and the scheduling decisions themselves are based on the information about the tasks that have arrived so far. And you see again here, static and dynamic scheduling approaches can be used for preemptive and non-preemptive tasks, and you have to consider the history for dynamic scheduling. And on the other hand, static scheduling or offline scheduling uses some previous knowledge about arrival times, about execution times, and about deadlines. So we can analyze it before the system is built or when the system is built and not when it executes. So the dispatcher allocates the processor when it's interrupted by a timer. And the timer, again, is controlled by a table generated at design time. So as you've seen here, at certain points in time, like 10, 17, 22, and so on, several actions happen in the system, like at time 10, task T1 is started, at time 17, a message is sent, at task 22, some tasks are stopped, and so on. So this is just a predefined list of things to do at defined points in time. And of course, you have to analyze the system, you have to know the properties of the system in advance in order to generate that schedule here statically. Now, when we have such a static schedule, we can build a so-called time-triggered system. And here again, we have a definition by Hermann Kopetz. And he defines that in an entirely time-triggered system, the temporal control structure of all tasks is established a priori by an offline support tool. So you have some tools that analyze your software, that analyze your constraints, and they start to generate this table, this temporal control structure. This control structure is encoded in something Kopetz calls a task description list, or TDL, and this contains the cyclic schedule for all the activities of the node, so of the system we are considering, or the processor in a system. The schedule considers the required precedence and the mutually exclusive relationships, so it keeps the order and it makes sure that no resources are used simultaneously when it's not possible. So the schedule considers the required precedence and mutual exclusion relationships among the tasks in such a way that an explicit coordination of the tasks by the operating system at runtime is not necessary. So we know all the precedence problems, the mutual exclusion conflicts in advance. We try to resolve them, or we do resolve them at compile time. So the operating system just has to activate the given task at a given point in time. And the component that does this is called the dispatcher. And this dispatcher is activized, as we've seen here, by a synchronized clock with given time units. And then it just considers the task description list and performs the action that's been planned for this instant. And according to some other colleagues, Xu and Parnas, pre-runtime scheduling is in many cases the only practical means to provide predictability in a complex system. So if you have a system consisting of lots of tasks, of perhaps many processes and so on, scheduling it at compile time before you run the system is the only way to guarantee timing constraints and so on. Now, if we have such a static schedule, it can be easily checked if the timing constraints are met, but the disadvantage is that the response to sporadic events may be poor because you just may have to wait until the point in time when the task handling your sporadic event is actually assigned to the processor. So now we consider two different approaches to scheduling. On the one hand, we have centralized scheduling. On the other hand, we have distributed scheduling. And when we consider mono and multiprocessor scheduling, we have simple scheduling algorithms that handle single processors, but when we have multiple processors, the scheduling algorithms get more complex. So we have several different algorithms for homogeneous multiprocessor systems, and in the case where the processors in such a multiprocessor system are getting heterogeneous, the algorithms are again different. So, for example, these heterogeneous platforms might include hardware accelerators as a special case, which have a completely different timing behavior than your usual processor. And the difference between centralized and distributed scheduling is that multiprocessor scheduling can either take place locally, so each processor decides on its own which tasks to schedule, or you can do it central on one processor, so there is just one processor that assigns for each of the other processors and for itself in the system which tasks to execute and when to execute them. So the question is, will this always work out? And the method to design this is to use a schedulability analysis. So we define a set of tasks to be schedulable under a set of constraints if such a schedule exists for the set of tasks and constraints. Now, to perform exact tests here is difficult because most of the tests are NP hard. So actually we define a set of sufficient tests. So we define to a number of tests that prescribe sufficient conditions for the schedule, and we hopefully have only a small probability that we are not guaranteeing a schedule, even though there is a schedule we just didn't find. And on the other hand, we have the necessary tests. We are checking necessary conditions. This is used to show that no schedule exists. There may be cases in which no schedule exists and we cannot prove it. Now, which parameters can we use to evaluate our scheduling here? Well, the first thing we need is a so-called cost function. Different algorithms we use aim at minimizing different functions here. And if we're considering the timing in a system, we can define the maximum lateness as a cost function, which is a maximum over all tasks in a system of the difference between the completion time of that task minus the deadline of that task. And this maximum lateness is less than 0 if all the tasks in a system complete before their deadline. So in this case here, we have two tasks and we execute T2 first. T2 finishes here, but actually its deadline is before that point in time. So the maximum lateness here is this red line, this red amount of time. On the other hand, T1 finishes before its deadline, so the difference between the deadline and the point in time it finishes here is negative. So here the maximum lateness is actually less than 0, so task 1 completes on time. And for the complete system, since we have a maximum here, which is larger than 0, we know that not all tasks complete before the deadline.